All right, welcome back, everyone. We are on day 3, so we're halfway through the week now at this point. We have a few slides to finish up on tidying data that we will start with this morning. And then we will get into our first case study, which is really going to tie together all the stuff that we've done so far around a single research question. But when we left off yesterday, we had just finished talking about pivoting, so making our data wider or longer, depending on what we needed for the context of that data. And now we're going to talk about two other functions, which are separate and unite. And so for these two functions, we have a couple of, I mean just one, data set that we're going to use for practice. So it's called scores in your notebook. Again, if you run that setup chunk at the beginning of the 06 tidy our markdown file, then you'll have the scores data that you can see in your console. And in this is some data from Harry Potter. So we have different students' names, their house, and then the score that they got on some test. And so the question is, what are the variables in this scores data set? So we have name, obviously. We have the house, which I have very helpfully labeled code for some reason. And then we have the score. But the name variable, like, is this one variable or two variables? Like, you could have name like we have now, but you could also have first name, last name as two separate variables. That would be helpful if you wanted to, for example, sort by the student's last name, which is a common task that people often need to do. If that was your use case, then you'd want this as two variables. So again, what is tidy and what is not tidy is going to depend on your purpose. Again, the goal here is to have one variable per column. And so it's just really thinking about, well, what are the variables that I need? Do I need first name and last name as separate variables, or is just one name variable fine for my use? So we're going to talk about how we could split this one column into two columns if we decide we want two variables. And then we'll also talk about how to put columns together. We're going to start with separate. And so separate, like all of the other tidy functions, the first argument is going to be that data frame of all the names and houses and scores. Then you specify the column that you want to separate. You say the names of the new columns that will be created. And then finally, what separates the pieces of information. And so by default, this is a regular expression, which I've mentioned a couple of times. So this is saying anything that's not a letter, we're going to use to split. And so the way this works in practice, we would have our scores, and we say we're going to separate the name column into two columns, first and last. And then we don't specify a separator, so it's just going to split it on any non-letter character. And so now we have two columns, first and last, where everyone's first and last names have been split into two columns. But we also get a warning, and it says it expected two pieces of information and additional pieces were discarded in one row, and that's row 4. And so we see that here we have Justin Finch. But if we go back to our original data, we see that his name is actually Justin Finch Fletchley. So what separate did was it split it at the space, because that was a non-letter, and then it split it at the dash, because that's also a non-letter. So it tried to split Justin's name into 3 pieces, but we had told it we were only expecting two pieces because we only specified two columns up here. And so that's why we get the warning that it discarded an additional piece of information in row 4. All right, but we can fix that. So we can specify a separator and we say only separate at space characters. And so now it does not split at the dash. So we get Justin's full last name, Finch Fletchley, and there is no longer a warning. So we can change how the separation is happening. All right, you can also change what happens when there's an extra piece of information, or conversely, not enough information. So there's an argument called extra, and by default, extra is worn. And that's what we saw happen when we had extra pieces of information. It went ahead and truncated. It took off that third piece of information, but gave us a warning that it did so. But there are other options you can use. So there is drop. Drop will do the exact same thing as warn. It will just only use those first two pieces of information and discard the third piece. But if you specify drop, it's not going to warn you that it did it. It'll just do it. And then the last option you have is merge. And that'll say we'll split it into two pieces, and we'll split the first time at the first character we're allowed to split at, and then everything else we're just going to merge together into that last column. So it'll split it into at most two pieces, since we specified two columns and into. Similarly, there's a fill option. So if there was a student who only had one name, like Oprah or Cher, just one name's all they need, you can tell R what to do. The default behavior is, again, warn, and that means that it'll fill a missing value in the rightmost column, and it'll tell you a warning, say there weren't enough pieces of information, we filled with missing values. The other option is to fill with missing from the right without a warning, or you can fill with missing from the left without a warning. So those are your options on how separate works. The opposite of separate is unite, and this is going to merge columns together. So again, it starts with our data, the data we pass into it, the name of the new column we want to create, and then all the columns that get merged, like take the place of this 3 dots. So all the columns we want to merge go there. And then we specify how we want the pieces of information to be separated. And the default is an underscore, and we'll see what this looks like. So here we have our separate names. We've split them out by first and last name. We can then unite the names. So we say unite, we want the new variable to be called full name, and we want to merge the first and last columns. So now we have a full name that contains first and last, and you can see that by default, R has separated the pieces of information with an underscore for every row. But again, we can change that. We can say to separate with a space. And so now the full name has spaces between the pieces of information that were merged together from those separate columns. Does anyone have any questions about separate or unite? No? All right. All right, so to recap our tidyr verbs that we talked about yesterday and today, there is pivot longer, which is going to take multiple columns and put them into 2 columns. There's pivot wider, which will start with your 2 columns and spread them out across multiple columns. And then there's separate to split a column, and unite to merge multiple columns. All right, and we'll get to play with those some more in our case study which is the next thing we will do. But that is the end of what I had for tidying data. Again, that's the end of this slide deck, but we'll continue using these functions, not only in our next case study, but throughout the rest of the week. It'll be important that we're able to manipulate our data like this. All right, so I will go ahead and switch slide decks. All right. So as I just mentioned, we are now going to take what we've learned about tidyr, dplyr, ggplot2. Those are the main ones, and we're going to put them all together around a single question. And along the way, we'll also be using some of the information we learned about data types yesterday as well. So to start, go ahead and open the case study notebook. So it's in your exercises folder, case study 1, and go ahead and run the setup chunk in order to get everything set up. And I will go ahead and do the same thing. All right. All right, so the data that we are going to be using comes from the 538 package. We saw this a little bit on Monday, but this package contains a lot of data sets that are behind the stories that appear on the 538 website. And then we're going to focus on one story in particular. We want to try and replicate this plot. So the question that they were looking at in this article was whether people are too superstitious to have a baby on Friday the 13th. And so what this graph is depicting is the average number of births on the 13th compared to the average number of births on the 6th and the 20th. So 1 week before, 1 week after, by day of the week. And so you can see here that there is a much bigger difference on Fridays, the 13th, than there are on, for example, Tuesdays or Wednesdays, the 13th. So we are going to take the data that they've put in the 538 package, and we're going to try and replicate this plot. All right, so first take a few minutes. You can discuss in the chat, or you can just jot some ideas down for yourself. Take a look at the data set that's here, US births 1994-2003, and that's part of the 538 package. Look at how that data is structured, what data is in there, and then think about the steps that we'll need to go through in order to get that data ready to make this plot. So take a few minutes, think about that, and think about what a good plan of attack might be. All right, so who has some thoughts about what we might need to do here? Or I can just go through what I think we should do. All right, so the first thing that I might do is just kind of look at the data, see what's happening in a single year. So this is 1994 to 2003. So I'm just going to look at kind of what the pattern is across the year. So you can see that there are like a lot of these weird spikes, which I'm going to guess are maybe weekends. We also see a big spike down here that I'm going to guess is Christmas. So probably not a lot of people giving births on Christmas. But this gives me just kind of a sense on what is happening in this data. And so if I think about what we have in this plot, we have day of the week on the x-axis, and then we have the difference in birth rate on the 13th compared to the 6th and the 20th on the y-axis. So what I think is that we need to end up with a data frame that looks something like this. We need the day of the week in one column of our data, and we need an average difference for the 13th in another column. And this, I will just clarify, like this is using a slightly different data set. So if you notice, the data set we're using is 1994 to 2003. This plot is 1994 to 2014. They did not provide a data set that had all of the years. They gave you two. It's like 1994 to 2003. And then there's another one that's like 2000 to 2014 or something like that. We're not going to combine those two data sets today, but you are welcome to try that as an exercise on your own after the workshop. So the data, the numbers that we get and the plot we make will look slightly different than this, but it's going to look pretty similar. All right, so this is what our data looks like to start. We have the year, the month, the day of the month, and the date. We also have the day of the week and the number of births that occurred on that day. And what we want to get to is a data frame that looks like this. We just have day of the week and then the average difference in the number of births for the 13th. And then there is some magic that needs to occur in between those to make that happen. And for us, that's going to be the tidyr is what's going to help us do this. So how can we do this? This is one potential process. So this is the one that we'll use in our exercises today, but there are many other ways you could go about calculating this information. But the way that I would approach it is to get just the data for the 6th, 13th, and 20th. So we want a comparison for the 13th. And for us, that comparison is going to be the births from 1 week before and 1 week after. So we need the 6th, 13th, and 20th. We're going to calculate our variable of interest, which is going to be the difference between the number of births on the 13th and the average of the births on the 6th and the 20th. And then we can average that difference by day of the week. So if that difference is greater on Fridays than on Tuesdays, for example, and then we will create our plot. All right, so this is the process that we're going to try and follow. So first, what we want to do is remove the date field. This is redundant. So if we look at our data again, because we have the year, the month, and the date of the month, we don't need the date field. Like all three of these pieces of information are in these three columns. So we can get rid of the date field because it'll get in the way later if we don't. And we'll look at where that would become problematic. And then we want to extract just the data from the 6th, the 13th, and the 20th of each month. So I'll give you a few minutes to work on this first step. All right. So let me pull up my R. Okay. So the first thing that we want to do is extract just the 6th, 13th, and 20th. So the way that we can do this is with filter. So we're wanting to filter the rows. So we can say filter to the date of the month is one of 6, 13, or 20. So we do that, and we now see that for each year and month, we now only have the 6th, the 13th, and the 20th. All right. Okay, so now we need to tidy our data. And there are two options for the ways that we could do this. We could have the days in rows as they are currently, right? Or we could put the days in the columns. So we could have, say, like the number of births on the 6th, the number of births on the 13th, and the 20th are 3 separate variables. So these are our two options. So now I want you to think about which arrangement is tidy. And think about what our next step is going to be. We want to find the percentage difference between the 13th and the average of the 6th and the 20th. So which layout of the data is going to make this easiest using our tidy tools? All right, so take a couple minutes, think about that. Feel free to throw an opinion or an idea in the chat, and then we can talk about how our tools will work with these formats of data. All right, does anyone have any thoughts on what would be easiest or perhaps more difficult? Amber says option 2 would be easier, and I agree. So if you think about option 1, if we were trying to take the average of the births on the 6th and the 20th, it'd be really difficult to do that in this format. So we'd be trying to take the average of 2 out of the 3 rows. And we could do that. Like we could write our own function to do this, but that's going to be really messy and a lot of work. So we're going to call that not tidy. With option 2, we can just use a mutate and do like the 6 column plus the 20 column divided by 2 to get our average. So this is going to be the easiest way to go. So that's what we will do. So what that means is we now need to pivot our data. So take a few minutes and we want to tidy the filtered data that we made in the last exercise. So pivot that to where the days are now in columns instead of in rows. All right. Okay, so we have our filtered data from our last step, and we now want to pivot it. And we want to go from 2 columns to multiple columns. We want to make it wider. We want to go from rows to columns. So that means we're going to use pivot wider. Our names are coming from the date of the month column. And our values are coming from the births column. So if we run that code, we now see our days of the week are now in columns with the births for each of those there. Okay, so now we need to calculate our variables of interest. So we're going to use mutate to add some new columns. We first want to calculate the average of the births on the 6th and the 20th. And then we want to calculate the percentage difference between the number of births on the 13th and the average of the 6th and the 20th. And you do have a little hint here. You'll need to put backticks. So that's right next to the 1 on my keyboard, at least, to the left of 1, around the days 6 and 13 to specify the column names. R does not like when column names are just numbers. So you have to put the backticks around it to let it know that it's a column name that you're specifying and not just the number 6. All right. So we are going to use mutate to calculate our variables. All right, so the first thing we need is the average of the 6th and the 20th. So I'll call this average 620. And we have to put the backticks around the numbers. So 6 plus 20. And so you can see that if I don't put the backticks, maybe you can see it's a different color right now. So R thinks it's a number. So if we put the backticks around it, then it goes from green to white. So it knows it's a variable and not the number 20. So if we do just that, we now have this average of the 6th and the 20th. And we can add another variable that will be the difference for the 13th. And we want the percentage difference. So the way that we get that is we calculate the 13th minus the average, the 620 average. And we want to divide that difference. So I'll put parentheses around that. Divide that difference by the average. So that'll be the percentage difference. And then if we just did that, our difference is these rather small decimal numbers. So I will take all of that and multiply it by 100, just so it's more on a percentage scale that we're used to. So we now have the difference for each month. So in January 1994, the 6th, 13th, and 20th were on Thursday. And the percentage difference, there were almost 3% fewer births on the 13th than on the 6th and the 20th. So that's what these numbers are telling us. Is this making sense so far? Kind of where we're going and how we're getting there? Awesome, great. Okay. Okay, so we have our output that we just looked at. All right, so we can take a look at the distribution of these differences by day of the week. So we can make a quick plot. And again, we're seeing Friday does appear to be a little bit lower than the other days of the week, as we might expect. But we're also seeing this outlier way up here. So there is one case where, because it's so much higher, there were actually way more births on the 13th of this month than there were on the 6th and the 20th. So we might ask ourselves, like, what is going on here? What's happening? So we can look and we can filter to just places where that diff13 variable we calculated is greater than 10. There's nothing special about 10. I just picked it because it was the only dot above 10, so I knew we'd catch it. And then we can see that this was for the month of September in 1999. And the 6th, 13th, and 20th of that month were all Mondays. Does anyone have a guess what might be happening in this month? So your hint is that the reason the difference is so high is because the average of the 6th and 20 is low. And that's being driven by the very low, relatively low number of births on the 6th. And so the 6th of September in 1999 was actually Labor Day. So there were relatively few births on Labor Day. And so there's possibly a holiday effect happening. And so we're not going to control for holidays as part of this. But that is something that we could do. And if we were trying to like write an article or something where we needed to be more specific about what was happening, that's something we probably want to consider, since this is going to be such a big outlier in our data. All right, so, but since we're going to ignore that for now, we can now calculate the average diff 13 for each day of the week. And so once you do that, you should have the data you need to create this plot. It will not look exactly like this yet. So once you get your data, just go ahead and make a bar chart or a column chart that replicates what's going on here. All right, so we'll take a few minutes to work on this piece. All right, so let's make this plot. All right, so we're starting with our same data set that we just looked at. And what we first want to do is calculate the average of this diff13 for each day of the week. So for that, we need to group by. So we'll group by day of the week. And then we can summarize and say that the average diff13 is going to be the mean of that diff13 variable. All right, and so this is the data frame that we were hoping to get at the beginning. So we have our day of the week in one column and the value of the bar height in the other column. So now we can go ahead and make our plot. So we can pipe that right into ggplot, and we map our aesthetics. So we want on the x-axis to be day of the week, and the y-axis to be the average diff13. And we will add a geom call. And so remember, because we've specified the y aesthetic, we use geom column instead of geom bar. So if we run that, we now have our plot. All right, was everyone able to get this plot? Still working, good. So I'll scroll back up a little bit to see the code as well. Awesome, good. All right, and so this is the hard part. Like at this point, we have gotten all of the numbers that we needed. We have the basic structure of the plot together. So from here on out, it's really just formatting. So how can we take this kind of default ggplot look, which is nice, but not as nice as that 538 plot looked. So I know we're right up on a break. So we will go ahead and break for 15 minutes. And when we come back, we will talk about how we can tweak all of the different theme elements in this plot in order to get something that looks closer to that original 538 graphic. So go ahead and take 15 minutes. We will come back at 10:15 Central Time, and we'll talk about how to keep working on this plot. All right, go ahead and give me a thumbs up or let me know in the chat that you're back. Awesome. All right. So when we left off, we had created this plot, which I'm now realizing is cut off at the bottom. So I'll pull back up my version. All right, so we had this plot. And now that we have all of our data organized and we have the values we need, we are good to start styling and theming this plot to look more professional, or in this case, like the original 538 version of it. All right, so let's talk about styling. So here on the left is our version of the plot, and on the right is what we're trying to get to. So there are a few things that are different here. So the first thing that I'm noticing is that our days of the week are in a different order. So ours are starting on Sunday, Theirs start on Monday. So that's one thing we can change. And then also their Friday is highlighted. So it stands out. So we want to color by Friday. So the way that we can do this is we want to reorder the x-axis. And the way that we do that is by releveling the factor variable. So we have the day of the week, and we're going to use fact relevel from the forcats package. And so we're going to relevel this day of the week factor, and we're going to put Monday first, and then Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And so since Monday is our first level now, it'll be that first bar in the chart. And then we're also going to make a new variable called Friday, and then we'll calculate that using day of the week equals Friday. So this will return a true if the day of the week is Friday and a false if it is not. And then we use our same ggplot2 code, but we add an additional aesthetic now. We want to color our columns by that Friday variable. So if it's Friday, it'll be a different color than the rest of the bars. So we can look at what that plot looks like. So now we have Monday, again, is our first column here, and Friday is a different color than the rest. This still does not look like the 538 graphic, so we've still got some work to do. So the next thing we can do is remove the legend and specify our colors. So our plot here, it added this true false for Friday. We don't really need that. There wasn't a legend in the 538 plot, so we're going to get rid of the legend, and we're going to specify our colors. So it's those pinks instead of the kind of orangish and blue that ggplot uses by default. And so the way that we do that in our geom call, we can add this argument that says show.legend is false. So it won't show a legend for these colors. And then we can use those scale functions that we talked about on Monday. So we're going to scale the fill of those bars with manual values. And I used a color picker tool to figure out which color those pinks are. And so these are some hex color codes. And so if we specify those colors, now our plot again is sized weird, but we're getting, you see there's no legend over here, and our bars are now the same color of the pinks. So now we have our comparison, and it's looking closer. We're getting there. But there are still some differences. So specifically, I want to change next our axes. So like here, our breaks are by 2s, their breaks are by 1s, and also our x-axis is on the bottom and theirs is on the top. So again, with ggplot, you can customize almost anything, so we can control that. So now our axes, so we're going to scale x, we're going to scale our x-axis, and it is discrete values, like each one is a day of the week. And we can add a position argument. So we say we want this on the top of the plot. So that'll fix our x-axis for us. And then on the y-axis, that's a continuous variable. So we're going to scale y as a continuous variable. And we want our breaks to go, we're going to make a sequence. This is another one of the functions that's built into R. This will create a sequence for you. And we want it to go from -6 to 0 by 1s. And so that'll get the breaks. And then we can specify our labels as 6, -6, 5, 4, 3, 2, 1, and then our 0 will be 0 ppt. And that'll be just like the 538 graphics. And finally, we can use the labs argument. So this is labels, like what do we want our labels to be? And if we look at the 538 graphic, it does not have any axis labels over here. So it doesn't say like the percent difference. That's what the percentage change over here, the PPT is doing. And it doesn't say day of the week at the top. It's pretty clear that Monday, Tuesday, Wednesday, Thursday are days of the week. So we don't need that label. So we turn those off with null. So we say the X label is null, which means nothing, and the Y label is null. So if we look at this plot, we now have no labels over here, or no titles. And we do have our axes now breaking by 1, and our days of the week are at the top of the plot. So we are getting even closer. The next thing that we can change is refining our axes even more. So one thing that is a little bit annoying to me are these black tick marks. So those do not appear in the 538 version of this, so we'll turn those off next. And then also, I'd like these numbers to be all aligned to each other. So the 0 is all the way out here because we added this extra label, but we can line those up. All right, and we do this with the theme. This is just the general theme. And again, I showed you this on Monday. There are a ton of different like minuscule things in ggplot that you can change. One of these are the tick marks. So we say axis.ticks, our element blank. That just means we don't want anything there. And then we can change the axis text for the y-axis, and we'll do the horizontal justification is 0. And so that's going to mean left aligned. So now we look at that. We no longer have those tick marks now. And all of these numbers, are lined up for us here. All right, and so there is in your handouts folder this theme elements reference, which is really useful for figuring out like what it is that you want to be changing. So you can see like here, this would be the axis line for Y, the axis title. So if you are looking at a ggplot and you're saying, I really want to like edit this one specific piece, this theme reference sheet is going to be really helpful for figuring out which theme element you're actually wanting to edit, because some of them are not always named intuitively. So hopefully this will help. And it also gives you some guidelines. So like it lets you know that element blank can be used to remove an element entirely, which is what we did for the tick marks. All right, so this is where we are at now. Excuse me. So we're getting closer, starting to look more like what we have on the right over here. So the next thing that I want to do is add a title and a subtitle, like 538 has over here. So again, this is part of the labs. So we turned off the X and Y labels, but we can add a title. So we say our title is Friday the 13th effect. And then our subtitle is this string of text, which also appeared on the 538 graphic. So that will add your title and subtitle. We also add to the theme now the plot title, which is a text element. And we say we want that to be bold and 1.5 times the normal size. So this rel is just a relative size, and it's 1.5 times the normal size. And that gives us this plot. So now we have our title, we have our subtitle, and our title is larger font and bolded. All right. So what is next, we want to do some color adjustments. So our biggest difference now is like we have this white background and white grid lines that the original does not. So we can change that as well. So we add more adjustments to our theme down here. Our panel grid minor, these are going to be our minor grid lines. So on our plot, we have the major grid lines, which are at the 4, the 5, and the 6. But then we also have these minor grid lines that are halfway in between each of those. And so we're going to use element blank to turn those off. We then change our panel background to be this hex color gray, and our plot background also. So the panel and the plot background control, one of them does this, what's already gray, it'll change that color, and the other one will change this white color. And I honestly don't remember which is which, but we can look. So the plot background is this larger area, I want to say. Yeah, I think the plot background is going to be this white area, and the panel background is going to be what is currently gray right here. All right, but when we add those color adjustments, we now have a graph that looks like this, and this is pretty darn close. So we have the gray background, the gray grid lines, we have our weekdays at the top and our labels over there on the side. We don't have kind of the 538 branding at the bottom, but that's fine. And we could continue tweaking this, like we could change this font if we wanted to. It looks like these tick marks at the top are like a little bigger in ours than they are for 538. But this is close enough for me. So this is where we will go ahead and stop. So does this kind of make sense on how you kind of just keep tweaking your ggplot like one step at a time, like every little element that you want to get to where you are? Or I guess get to where you want to be. Awesome. And so as you can see, like ggplot lets you do a whole lot, but as you keep adding more and tweaking more, like we have a lot of ggplot code here. Like there's a lot of lines of code to make that plot. So the plus side is that you can customize your plot pretty much every way you want to. The downside is you can end up with a lot of code to make that one plot. But I think it's worth it to get the plot that you want. All right. So these are some extra challenges for you all. We won't go through them right now. If you want to try them and see what happens, I would encourage you to do that. If you want to talk about them at office hours, like feel free to sign up for those times we can talk about it. But a couple just food for thought is if we wanted to merge those two US births data sets. So we only used the 1994-2003 version. If we wanted to combine across both of them, what would we need to do for that? How would that make our pipeline different? And then also if we don't remove the date column, so we removed that at the very beginning because I told you it would cause problems later. If we didn't remove it, where would that break our pipeline and why is it doing that? So those are some things to think about. We won't take time to do those now, but those would be good exercises for you all after the workshop to keep growing your data skills. All right, so that is the end of our first case study. Does anyone have any thoughts, questions, comments, concerns before we move. This is kind of the biggest transition point of the workshop. So far we've mostly been managing data, doing like summary statistics and stuff like that. And after we go into our next slide deck, we're really going to shift into modeling. So fitting some different types of models to learn from our data. So we'll keep using these tools, but the focus is going to be much more on estimating those models and learning from them, as opposed to just managing the data. All right. Well, I think we will go ahead and pull up the next slide deck. If I can find it, here it is. All right. So we're now going to start talking about prediction. We have two main topics for the rest of today. One of them is this slide deck, which is about prediction, and that's more focused on continuous outcomes. So we'll talk about linear models, like a normal linear regression, and then we will this afternoon talk about classification. So we'll look at what happens if we have a discrete outcome and the type of models we can fit in that scenario as well. All right, so let us start by go ahead and open up the prediction notebook, and that's in your exercises folder. It's the prediction, and go ahead and run the setup chunk, and I will do that same thing. All right. So in our graphic that we've been looking at a lot this week, we will start to see it less now because we are in this model part of our circle here, and we're going to kind of stay in this model part for the rest of the week. So you'll see some more charts that are similar to this that kind of describe the modeling process that we're going to go through. But for the most part, we'll be hanging out right here for the rest of the week. All right, so there are a few data sets that we're going to use. The one that we're going to focus on for now is called Ames housing. And so this is going to include descriptions of just under 3,000 houses that were sold in Ames, Iowa between 2006 and 2010. It contains things like square footage of a house, its lot size, its sale price, all sorts of different things. So this code is in your setup chunk. So you should have this Ames data object. If you type Ames in your console, you should see the data set after you run the setup chunk. We can take a quick look at Ames. It tells us there are just under 3,000 rows, and there are 74 columns. So there is a lot of information about these houses. It has like the type of street that it's on, whether it's a paved street or not. the type of utilities, the shape of the lot, the building type, the house style. Like there's a lot going on here. We have 74 variables about each of these houses. And what we are going to do is try and predict the sale price of the house from these different conditions or these different variables. So one way to do this in R is to use the LM function. That just stands for linear model. We're going to fit a linear regression. And we say we are going to predict the sale price from the living area. And we're going to use the Ames data set. And so this will fit a linear regression for you. And if we look at that, we see we get the formula that we submitted and we get our model coefficients. So if you've taken a linear regression class before, this will look familiar. You have your intercept, which would be the predicted sale price when this living area is 0, and then the expected change in sale price for each 1 unit increase of this living area. So in R, very easy to fit a linear regression model. Where we're going to talk about a few different ways that we can look at this question. So again, LM is for linear models with ordinary least squares regression. And I guess I should specify the GR living area is the total above ground square feet of the house. So it does not include basements. Not super important, but that's what the GR is standing for. All right, and this is like based on formula syntax. So we have our formula here that we submitted to the LM function, or we can add things to it as well. So here we've added, we're going to predict the sale price from the living area plus the number of full baths that we have in the house. Excuse me. So like a lot of modeling functions in R, LM is going to take a formula that describes the relationship that we want to model. So formulas are always divided by a little squiggly or tilde, and they contain the bare variable names, which just means we don't have to put quotes around them. The variable on the left, again, is your independent variable or your response variable, and the ones on the right are the predictors or the dependent variables. And they all live in the data set that gets passed to the data argument of the formula. So again, here, and we specify data equals Ames. So all of these variables should appear in the Ames data set. If they don't, you'll get an error. So a formula can have one variable on the right side of the equation, or it can have multiple on the right side of the equation. Alternatively, you can also just put a period here. So you can say sale price, squiggly period, and that just means predict sale price from every other variable in the data set. You can also tweak your formula. For example, if you put 0 plus living area plus full bath, the 0 will tell it to not fit an intercept. If you wanted to do that for your model, you can also add interaction terms. So we could say living area plus full bath plus living area colon full bath, and that would add the interaction between the two. Or instead of a plus sign, we could do an asterisk for multiplication, and that would tell R to add both of the main effects plus the interaction, right? So there are a lot of ways to specify formula specifications in R. If you type question mark formula into your console, that has a lot of details about how we can specify formulas and what they will do and what they mean, right? So earlier we saved our linear model to this LM-AIMS object. And when we looked at it, right, if we look at LM-AIMS, we see that all it did was shoot out our coefficients, which is nice, but like ideally we'd like to see some more information about our model than just the coefficients that got estimated. And the way we can do that in R is with the summary function. This is not summarize from dplyr, it's summary, so it's different. But this will display a summary of the results of the model. So if you do summary of LM-AIMS, then you get this nice printout. So it describes the distribution of your model residuals. It gives you more information about your coefficients. So these two numbers here are the coefficient estimates that we saw earlier, but now you also see standard errors, your test statistic and p-values for those coefficients. And you also get some information down here about your R squared and your F statistic. Right. So a lot of information about your model can come from summary. All right, so I want to take a step back now and think more generally about like what actually is a model, right? So a model is just going to be a low dimensional description of a higher dimensional data set. And it can be many things. So it can be a straight linear line, it could be a curved line, like a cubic regression, or it could be like almost like a parabola or like a lowest line. So all of these are models. There are different ways to describe your data. And so generally you have like your data, it goes through like some black box algorithm and you get like some model function out. And you might ask like, what is the model function? And so that is your linear line or your curved line or your decision tree, whatever type of model you're fitting, the model function is what's going to come out of that algorithm. You can also estimate the uncertainty associated with it. So we can figure out not only what that model function is, but how certain we are around those predicted values. We can look at residuals. So how far away were our predicted values from our observed values? And we can look at the predictions. So what are the predicted values actually, right? And so the question is like, what makes an algorithm good? Because there are a ton, like there are so many different models that you could fit. The question is like, which one should you be using for your data? And that's really what we're going to try and answer this week. We're not going to get too deep into like the statistics of how these methods actually work. This is not a kind of like statistics class, and I'm not a statistics professor. But the question I want to help you all answer is, after you learn different models in your classes, like how can we evaluate which model is best? So for example, if you learn about logistic regression and maybe like random forest or another predictive classification algorithm, like how can we choose whether a logistic regression or a random forest is best for this particular set of data? So we're going to learn the tools on how to fit these models in the tidy models framework, as well as how to evaluate and compare our models to figure out which one is going to serve us the best. So that's really where we're going through the second half of this week. Right. So statistical modeling is going to be an extension of hypothesis testing. So we have a hypothesis that hopefully explains reality. From our hypothesis, we form a model, which then hopefully matches our data. And whether it does match the data or not depends on whether we are going to reject or accept our hypothesis, right? And so really the question that we're asking is whether the model that we have proposed is a reasonable representation of the world given the data that we have collected. And so the hypothesis that we have is going to determine a few things. It will tell us which data to use, hopefully which model to use, or at least which set of models we should consider, and then how to assess the model. So for example, does the model that we're using perform better than a null model according to different statistical criterion or tests? And so this is going to be an important place to start, especially when we get into more of the machine learning methods, because machine learning is really not a lot like hypothesis testing, right? So hypothesis testing is very much concerned with explaining the world, looking at causal models, whereas machine learning is much more focused on prediction, like what's giving us the best predictions for this particular problem. All right, so we start with some old data. So this would be like data we have collected, and we have a model that we want to fit. So we train this model and we get our estimated model, and then we have new data and we feed our new data into this trained model and we get predictions, right? And so this is kind of like the goal of any machine learning method, is we want to take our data we have and make predictions for the future. And based on those predictions, we might improve our model so that we can better predict future behavior. All right, and all of this is going to be done for us with the tidy models framework and the tidy models set of packages. So tidy models is very much like the tidyverse, in that tidy models is a suite of packages. So there aren't really functions in the tidy models package itself that we will use, but there are a bunch of packages within tidy models that we'll learn about as we go through the rest of this week. And just like there was an R for Data Science book that described a lot of what we talked about earlier in the week, there is a book called Tidy Modeling with R, which describes this software, how to use it, and best practices for modeling. The book is not done yet, but it is available for free online. So there are large chunks that are complete and more will continue to be added. So even though it's not done, that'll be a really good resource for all of us. All right, so what is the goal of machine learning? The goal of machine learning is going to be to generate accurate predictions at the highest level. Like that's what we want to do. So for LM, we can start with a prediction. So to predict, we have to have two things. We need a model to generate predictions. That's going to be our LM Ames model. And we need data that we can predict, right? So step one is to train the model. So we have our data, we have our model, and then we need to train it. And so for linear regression, there are a lot of ways to do this in R. So one way is with LM. That's the one we looked at earlier. You could also use GLM. So GLM is going to be for general linear models. So for example, if you wanted to fit a logistic regression, you could use GLM, but you can also fit just a normal linear regression with GLM. If you wanted to use some form of regularization, you could use GLIMnet or GLMnet. That would be used, for example, if you were doing like a lasso or a ridge regression. If you want to do a Bayesian regression model, you can use RStanArm or BRMS. If you're using TensorFlow, you could use Keras. If you have a really, really large data set, you can use the sparklyr package to set up a Spark interface, and many more. There are a ton of different engines that are possible for estimating a linear regression. And so within our tidy models framework, we need a way to specify not only what our model is, but how we want to estimate it. So that means like which engine are we going to use? And so for that, this is our first tidy models package, and it's going to be parsnip. So you will notice as we go through this, a lot of the tidy models packages are food-based. So we get like these cute little characters, like this little parsnip guy, I think is quite adorable. But the downside is like, this might also make you a little hungry because we're going to talk a lot about food. But lunch is not too far away. So parsnip is what we're going to use to specify our modeling objects. We're going to specify our models with parsnip. And again, there is a chapter in the Tidy Models with R book already called Fitting Models with Parsnip that kind of walks through this as well. All right, so to specify a model with parsnip, we first are going to pick a model, we're going to set the engine, and then we're going to set the mode if necessary. So the mode is really whether we are doing a continuous prediction or a classification problem. So some models can only do one, so we don't need to set the mode. Like a linear regression is not going to do classification for you, so we would not need to set the mode there. But a random forest model, for example, can do both. So we would need to tell whether we were going to do a regression model with a random forest or a classification model with a random forest. And we'll see that more later this week. So to specify a model with parsnip, we first choose our model type. So here we've said we're going to fit a decision tree. That's our type of model. We then choose our engine. So this is the R package that you want to actually do the estimation. So here the engine is C5.0, and we set the mode. So this would be a classification decision tree using the C50 package. Similarly, we could look at a nearest neighbor model. So we can specify a nearest neighbor using the KKNN package, and this is going to be for a regression model. And that should not have a pipe at the end, but so all of the parsnip models are going to follow the same sort of format. It's going to be pick your model type, pick your engine, set your mode. All right, so to pick a model, there are a ton of different options, but they're all listed at this website. So we can go here. And you can see that for all these different parsnip models, they have a searchable table that has titles, model types, the package, the modes that are available. So you can say these ones only do regression. If you were doing a bagged Mars model, which I'm not familiar with, but it exists, it can do classification or regression. So you would need to set the mode in those cases. But there are, as you can see, a lot of different model options. So I think most of the models you would try and fit would be supported. But you just have to come in here to figure out what exactly it is you need to specify. All right, so for a linear regression model, the model specification in parsnip is linear reg. And so that's going to specify a model that uses linear regression. So we can say linear reg and the mode is equal to regression. So you can set the mode within the model function, or you can use the set mode function that we saw a second ago. Either one will do the same thing for you. And you also might specify a penalty term or a mixture term, depending on your particular flavor of linear regression. So again, if you were doing like a penalized linear regression, then you'd specify a penalty term here. But if you're just using like ordinary least squares, that would not be necessary. So again, the mode here's regression, and it'll have a default mode if a mode is necessary. And then the penalty and mixture are model hyperparameters. All right, so the next thing you do is set an engine. And the engine is going to be what powers or implements the model. So here, if we wanted to use the LM function as our engine, because that's not from a package, it's just available within base R, we can say that our engine is going to be LM. Like that's what we want to use to estimate our linear model. And finally, we would set the mode if needed. So we can use the set mode function to do that and say mode equals regression. But again, you don't have to do this if you are specifying that in your original linear regression model call. All right, so that is a very quick, high-level overview of how to specify a model in parsnip. So now we're going to play with this and get our hands on it to specify our own model. So I want you all to do in your notebook is to write a model specification with the pipe. All of these are pipe friendly. So we want to create a model that uses LM to fit a linear regression. And we want to save this model object as LM spec. All right, and after you do that, look at the object and see what it looks like. Yeah, so we'll take a few minutes to work on this, and then we'll see what the model specification with parsnip is actually doing. Okay. So to make our linear regression specification, we want to call it LM spec. So we can use this arrow to save our object as LM spec. We're going to call it, we're going to use linear reg because we want a linear regression model. And we're going to set the engine to be LM. Right? And we don't need to set the mode because it can only do regression. Right? And so if we look at LM spec, we see that it is not much here. It's just a linear regression model specification. And it's using regression because that's all it can do. And it says that our computational engine is LM. So that's what's going to be used to actually estimate the model. Was everyone able to see this LM spec output? Because we'll be using this model going forward. So I want to make sure that everyone has it specified. Yes, good. Good. All right. So now we can use fit. So this is the fit function is going to train your model and it will return a parsnip model fit. So we, the way we do this is we use the fit function and we say our model is the specification, the parsnip model specification we just created. We give it a formula, which in this case is we're going to predict sale price from the above ground square footage. And we give it our data. So the data is going to be used to train this model. Right? And because we're using the LM engine, this should give us the same answer as just using LM would. All right. So we want to check that. So you can run this code, get your LM fit, and then verify that that is giving you the same results as just the plain LM code at the bottom here. Okay. So if you run this code at the top, you should see this output. So you see that this is a parsnip model object. It gives you some information about how long it took to actually fit the model. In this case, not long at all. It gives you the function call that it actually used. So you can see that it used the LM function like we told it to, and the formula and data that was specified. And we get our coefficients again. And we can see that this parsnip model object gave us the exact same coefficient estimates as what we got when we used just the LM function. Right. And so at this point, you might reasonably be wondering, if I can fit this model with one line of code, why am I going to all the trouble of specifying a parsnip model object and then fitting it when I can do that all at once with LM? Which is a valid question. And so the answer is that while LM works this way, if you're doing a different type of model, it might have very different type of syntax for how to estimate that model. It'll have different arguments and different ways that the data needs to be structured or specified. And so parsnip allows you to specify all of these different models in the same unified sort of framework. So it's always just the type of model, the engine, the mode, and you can specify any type of model like that and then fit it using the fit function. And so if you know in your research, like I'm only ever going to fit linear models, that's all I need to do, then parsnip might be kind of overkill for you. Like that's a lot of code that may not be necessary. But if you're going to be fitting a lot of different types of models, then parsnip gives you a way to specify those models really easily without having to learn the syntax of a bunch of different packages. So that's why I like to introduce parsnip, and that's why that's what we'll be using for the rest of this week. All right, so we have our data, and we add our model, and that gives us our fitted model, right? And so this is where we're at in our little process here. And we have our data, we've trained it, so we have our trained model, and now we want to make predictions. And so to do that, there is a predict function. And predict works by taking your fitted model. So LM fit is the parsnip model we just estimated. And we say use this model to make predictions for a new data set. And here we've said our new data is Ames. And so this is actually just going to give us predictions for the data that was used to estimate the model. And that's fine. So even though it's called new data, we're using the same data, but that's just what the argument is called. And so if we run that, we can predict from LM fit our new data, and it'll give us a tibble back that has one row for every row in our data that was specified with the predicted value. So you can see the predicted value for each row is what comes out of here. And we could plot those if we want. So we have, this is just a subset of the data, but we have our fitted linear regression line, and the predicted values are the ones that are going to fall right on that line with our observed value around it. All right, so now, again, I have some template code for you all to complete. So what I would like you to do is use the predict function, and we want to take our linear model that we estimated and get the predicted sale prices. You can save that as price pred, the predicted price. And then use mutate to add a column with the observed sale prices. Right, so this predict function is going to give us just that one column back. And so here we want to add the observed data as well, so we can directly compare the predicted to the observed values. All right, so it'll take a few minutes to work on that. All right. So if we look at the solution, we have our lm_fit object that we already created. So we're fitting our linear model specification to this formula with the Ames data. To predict, we take our fit object and we can pipe that directly into the predict function. And we specify that our new data is Ames. And then to create our truth variable, we use mutate to add a variable. We're calling it truth. And this will extract the original sale price from Ames. So if we have the Ames data and we use the $, then it's saying this is the column from Ames data that we want to take out. So this will give us just the vector of the observed sale prices, which are then compared to the predicted sale prices. And that gives us this new price pred data, which again has the predicted values in the first column, and then the truth or the observed values, the observed sale prices in the second column. Was everyone able to get those predicted and observed scores into their data or into a single data frame? Thumbs up, good, awesome. Okay. So we started with our data and our model, and that gave us our fitted model. Then we can take new data with our fitted model to get predictions. So earlier we said that the goal of machine learning was to generate accurate predictions. But now we need to know what to do with them, right? How accurate are they really? So we'll focus now on the accurate part. Okay. And so the I guess axiom, I guess the name of the slide, is that a better model is going to mean that there are better predictions or a lower error rate. This is not always the case. Like there are places where you can get really good predictions, but maybe not have such a great model. But for the most part, if you're able to generate better predictions, you're going to have a better model. So we have our predictions here. These are the ones that fall directly on that fitted line. And then how far off our observed values are from the predicted values are the residuals. And so the residual is that difference. So the length of that pink line between the predicted and the observed values. All right, and so the y hat here is what's often used to refer to the predicted value, and then the y without the hat is the observed value. And this is going to refer here to a single residual. So the predicted value for case I or row I minus the observed value for row I. And since residuals are errors, right, that's how far off we were, the sum of the errors would be a good measure of the total error, except for two things, right? So if we just sum up all of the errors, what is something that could go wrong here? So the first thing that I think that goes wrong, yep, canceling each other out. We're going to talk about that one in just a second. The first one that I want to talk about is like what a sum is actually doing. So when we have this, the sum is going to increase or decrease, and we get to cancel each other out every time we add a new data point, right? So that means that models fit on larger data sets are going to have bigger errors than models fit on smaller data sets, just because there's more elements being added together, right? And that doesn't make a lot of sense. And we'd like to have everything on a similar metric. So that leads us to working with like the average error. So what's the average error across all the data points? Okay. So we can like sum them all up and then divide by the total, and that'll give us our measure of average error. But then, as Amber noted in the chat, the positive and negative residuals are going to cancel each other out, which is not what we want. If there's a lot of positive error and a lot of negative error, and we say, 0 error, great. But actually, no, there's still a lot of error there that we're missing. So one way we could do, or we could get around that, is taking the absolute value. This is what's referred to as the mean absolute error. The problem with mean absolute error is that mathematically they're very hard to work with. So if you've ever taken a calculus class and talked about derivatives and integrals, you may know that absolute values cannot be differentiated at 0, which doesn't matter to us because we use computers, but it mattered in the past. And so as a result, a lot of people don't use this just for historical reasons. So instead, statisticians usually will square the error. So when you square a number, it'll always be positive. So instead of taking the absolute value, people tend to square the error. This also has some convenient properties. One, it's differentiable, and 2, this actually represents the standard deviation of the residuals around 0. So we use the square, the average squared error here, but then our problem, just never-ending problems here, is that our error is actually on a different metric than our data, right? It's been squared. So we have like square of the error that actually exists. So the last thing that we do here is take the square root. So we square all of our residuals, sum them up, take the average, and then finally we take the square root. And this is called the root mean squared error. And this is a very popular way of assessing predictions. And so you will see the root mean squared error come up a lot when you're looking at model evaluations. And again, this is what this actually represents when you calculate it, is the standard deviation of the residuals around 0. So if you have a small RMSE, it means there's a small standard deviation, which means there's not a lot of variance around those predictions. All right, so they're all very close to the predicted values. If you have a large RMSE, it's a large standard deviation. So think about a large distribution of those residual values, which means you have more error there. And so there is another package within the tidy models kind of ecosystem called yardstick. And yardstick is what we'll use to evaluate our models. So it has a bunch of functions to calculate different model performance metrics. One of these is the root mean squared error. So we'll use the RMSE function from yardstick to evaluate our models. And again, there is a chapter using yardstick in the tidy models with our book that talks a lot more about all the different metrics that are within yardstick. All right, but we're going to focus on RMSE. And so this is going to calculate the root mean squared error based on 2 columns in the data frame. So RMSE is going to take a data frame that has values in it, and then you tell it which column has the truth and which column has the estimate. and you tell it that, and it will give you the RMSE for your data. So this is what we did previously. We fit our linear model. We then created the predictions. So we had our predicted value, and then we added the truth to it. And here I've called it price truth, so the true price. And so we'd say, all right, we're going to calculate the RMSE using the price pred data. The truth is in the price truth column, which is what we specified as our observed values. And then the estimated score is in the .pred column. So we run that and we get the metric for our model. So it says we calculated the RMSE with a standard estimator, and this is our estimated root mean squared error, 56,505, which is hard to think about out of context. Like on the one hand, 56,000 sounds like a very large number, but if we're dealing with house prices that are in the hundreds of thousands, maybe that's not such a big number, or maybe it is. We don't really have anything to compare it to at this point yet. Ideally, what we would do and what we'll continue to do as we go through this week is we'll fit multiple models and then compare these different metrics. So does a different model give us a better RMSE? In other words, giving us better predictions. Okay, so we had step 1 was to train the model. Step 2 was to make predictions. And then step 3, which we just saw, was use those predictions to create different model metrics, which in this example was the RMSE. All right. So revisiting our little chain of modeling, we started with our data plus some theoretical model that we had to train a model. We used our fitted model plus some new data to make predictions. And then we used our observed data plus those predictions to get our model metrics. Okay, but a model does not have to be a straight line, as we saw earlier. For example, we could do a regression tree. And in this case, it would fit a model that looks something like this, where all of the houses that have an above ground living area between these two values would have the same predicted score, and then the same predicted score for these. And so it's a stepwise function, basically. And then you calculate your new set of residuals from the regression tree model, and you could compare the RMSE between this regression tree model and the linear regression model. But the question is, like, do you trust it? Like, if you have this model, do you trust the predictions that are coming from it, right? Because this has, I guess, like 3 steps, 1, 2, 3 steps. We could fit a regression tree model that had like 10 steps or 12 steps. But the question is, like, are you going to trust the predictions that come out of it? And this is what we can call overfitting. Like, are we overfitting our model? And this becomes the danger of, like, better predictions do not always necessarily mean a better model. So here we have our linear regression model is this blue, the straight blue line. But we could fit a curve to it. That's the pink line. And this pink line is pretty close to our linear regression line. But we could loosen that up. We could fit a curve that looks like this, or we could fit a curve that looks like this. And so as we keep adding, in this case, polynomial terms to the model, the curve matches more and more of the data points, like the residuals are going to be decreasing but the question is at what cost? So for example, if you look at this yellow highlighted point, it's much further away from this curve than it is from this curve on the right. All right, so drop your thoughts in the chat or think to yourself, between these two models here, which model is going to have the smallest residuals? And then if you were to use this model to predict new data, which model is going to have the lowest prediction error and why? So take a couple minutes to think about that, and then we'll discuss it together. Okay. So yes, Amber, thank you for throwing that in the chat. So the one on the right will have the smallest residuals, and the one on the left will have the lowest prediction error, and that is correct. So if we actually look at the RMSE for these models, this is, as we add polynomial terms to the model, our RMSE keeps going down, like we're fitting closer and closer to our observed data. But if we look at the out of sample prediction error, it goes way up as we keep adding more and more terms to the model. And the reason for this is that we're overfitting to our data, right? We have outliers in our data, as Amber mentioned, that are drawing that polynomial curve in crazy directions, which does not generalize to new data outside of our model. So how do we get around this problem? So another axiom for us is going to be that the best way to measure a model's performance at predicting new data is to predict new data. Okay. So our new goal of machine learning is to construct models that generate accurate predictions for future yet to be seen data. So we don't want to just get as accurate of predictions as we can for our current data set. We want to make sure that we're going to be able to generate accurate predictions for new data that comes in. Right? We want to make sure that we're able to adequately explain what's happening as we continue to get new data. And this is described a little bit. There's a book that's available for free online on feature engineering. that talks about this goal of machine learning as well. The problem though is that we need new data, right? It's like we've collected a data set. If we want to predict new data, then we need more data, or we need some way to simulate new data or pretend like we have new data. And so the way that we'll do this in R and the way that this is done in practice a lot is to hold some data out, right? So we have our original data set and we will split it into a training set that we use to fit the model and then a testing set. So the observations that are in the testing set are not used when we fit the model. And then we use our fitted model to predict that data from the testing set and compare those predictions. So the function we will use in R is called initial split. And this is going to split your data randomly into a single testing and a single training set. And so the way initial split works is you give it your data that you want to split, and you tell it the proportion that you want to keep in your training set. So here we'll use 75% of the data for training, and the other 25% will be used for testing our model. And so if you do this initial split function, you get a split object. So here aim split, which tells you not a whole lot, but it tells you the total number of cases you have in aims. So this is the 2,930 that we've seen before. And because we kept 75% in the testing set, says we're going to use 2,198 rows to train the model, and that leaves us 732 rows to test the model on. So the downside of doing this is that you have less data to fit your model with, right? We're not using the whole data set to train our model, but it gives us a way to assess our out of sample predictive power. How good are we going to be at predicting new data that comes in? And we can extract the training and the testing sets from the split object. So if we do training on this aim split, it'll give us a data frame that includes only those 2,000-ish rows that are used for training. And this testing will give us the 700-ish rows that we're using for testing our model. So for example, we can make a new object called train set that is the training of the split object. And so this now has all of the same columns, but now only has those 2,198 rows that we're going to use to train the model. Okay. So now that we have this, I forgot I had this, so I kind of already gave you all the answers. Now that we have the training and the testing sets, which data set are we going to use for fitting, and which do we use for predicting? And I already gave it away that we'll use the training to fit the model and the testing to look at our out of sample prediction. All right. So again, I'm really just going to drill this in. We train the model as our first step. We're going to make predictions, and then we're going to compute metrics. And the functions that we use to do this are fit, predict, and RMSE, at least for our linear regression model. But now we're going to switch it up a little bit. Our new step one is to split the data. So we split it into quote unquote old data and new data. That's going to be our testing and our training sets. Then we're going to use the training data or the old data plus some model, in our case, a linear regression, to get a trained model. And then we're going to use the new data plus our trained model to get predictions. And then we take the observed data from our testing set with our predictions to compute metrics. All right, so this is our new workflow that we're going to start following. All right, so let's give this a try. Um, this is a lot of code, but what I would like you to do is use the initial split, training, testing, and the LM functions and RMSE. We want to split the aims into training and testing sets. We want to extract the training data and fit a linear model to it. And then we want to measure the RMSE of our model using the testing data. So I've given you some template code here. So what I would like you all to do is try and complete that code to estimate the RMSE from our test set. All right. Does everyone have enough time? We're ready to start talking about a solution? I know it starts to get a lot more code heavy. There's a lot, at least longer exercises as we start to get into the modeling, just because it requires more code. So make sure everyone has enough time to complete it before we move on. I'll go ahead and start talking about the solution, and you can tell me if you need more time or not. So to start, we create our initial split object, call that aim split, and then we extract the training and the testing data using the training and testing functions, and I called those aims train and aims test. We then fit our linear model. So we use the same parsnip lmspec model specification that we created earlier and our same formula. But now we say we want to train that data, or we want to fit this model using only the aims train data. So that will fit a model using just our training set. And then to create the predictions is the same code we used earlier. So we still use the lm fit, but now when we use the predict function, we say that we want to predict, but our new data is this aims test. So the data was not used to train the model, but we're going to use that for predictions. And now when we create our new truth column of our observed values, we're going to pull those out of the aims test as well. So we have our predicted values for aims test and the observed values for aims test. And now when we do the RMSE, we see that we get an RMSE of just over 59,000. And just for comparison, when we fit our model using all of the aims data, our RMSE was about 56,000. So it's a little bit higher, but pretty similar overall. And we might expect it to be higher. We are using less data to fit our model. So that will change our model coefficients a little bit. And maybe we were a little bit overfitting earlier. Maybe that's why our RMSE is lower. But it's hard to say from just one resample. But we can visualize this. So we have our original, or this is just with our training set. The RMSE is 55,000 and the testing set is 59,000. So again, it is good to check your predictions against unseen data to make sure that you're not overfitting your model. So the way that our process is now working as we continue to iterate through this chain of how to do our modeling, we start with our old data, X our predictors and Y our predicted value, and some model that we train to get our fitted model. We then take new data plus our fitted model to get predictions. Then we take the observed data from the observed scores from our new data with those predictions to get our model metrics. And one thing we have not talked about is how much data you should set aside for testing. So how much are you going to keep for training and how much are you going to keep for testing? And there's not really a right or wrong answer here. Some of it is going to depend on how much data you have in your total data set. So in our aims data, we have almost 3,000 rows. That's a pretty good data set for us to work with. But if you only have 50 data points, then it's a much harder question, right? So if your testing set is small, your performance metrics may be unreliable. So like if you only have, again, 50 observations, you use 45 of them to train your model, then you're only evaluating performance on 5 individuals. Depending on which 5, there's going to be a lot of variance in what your model metric looks like. Conversely, if your training set is too small, your model fit may not be very good. So if we only fit our model on 5 people and keep 45 for testing, we're probably not going to get a very good model from those 5 people. So it is a balance, and there's not really a right answer. By default, the initial split will do 75% in training and 25% in testing. But again, you can control that, and that's something that you'll have to consider when you are fitting your own models. But one way we can help with this is to use stratified sampling. And I know we're coming up on lunch, and this is actually a pretty good breaking point. So why don't we go ahead and we'll break for lunch a little bit early. We'll stop now. We'll still come back at 1:30 because I know some of us have meetings that they scheduled for our lunch hour. So we'll just take an extra few minutes for lunch. So we will come back at 1:30 Central Time to talk about stratified sampling. But have a great lunch. And as I have done the past couple of days, I'll leave the Zoom open. So you're welcome to stay logged in, or you can exit and log back in at 1:30. So have a great lunch. Right, welcome back, everyone. I hope you all had a good lunch. So before lunch, we were talking about this issue of how to pick the size of your testing set and your training set. And there are potential problems for either of these if they're too small. And the biggest issue is that you want to make sure that not only do you have a sample size that's going to support the work you want to do, but you also want to make sure that that sample is representative. And so one way that we can control this, or hope to control this, is through stratified sampling. So for example, if we have a data set like this one, and we split it into a testing and a training set, hopefully we would have something that looks like this. So here the training is in the blue and the testing is in the pink. And they're both like pretty similar. Like they seem to be evenly distributed across the data, which is what we would hope if we're just drawing a random sample to pick which is in the testing and which is in the training. But that might not always be the case. So like just randomly, we could draw something that looks like this. So all of our training data is for low or houses with a low area size, and the testing data is everyone with a large house. Or we might end up with something like this, where all of our training data were houses that sold for a relatively low price compared to houses that sell for a high price in our testing set. Or we could have very low houses in our testing set, low price houses in our testing set, or we get something that's even more extreme and all of our testing set data is in the smallest area, smallest price. Probably not going to get very good predictions if our testing data and our training data look so different from each other. So one way that we can help ensure that our data is balanced in our testing and our training data is to use stratified sampling. So instead of just doing a random sample across all of our data, we can do a random sample within each strata. So we have our data that starts as kind of a blank slate. And we say, okay, from this first strata of price, we're going to sample 75% to be in the testing or to be in the training, and the other 25 to be in the test set. And then we move to the next strata, and we do the same thing. Give me 75% from this strata to be in the training and 25% to be in the testing. And we keep going for strata number 3 and then strata number 4. And we could do that for more than 4 strata. Here, I've just done 4 because we don't have that much data in this graph, but you get the general idea. So the goal is to divide your data up into different segments and then do your sampling within each segment to ensure that there is representativeness of your data across your testing and your training sets. And so in our sampling function, so we use the initial split function to make our testing and training sets. And so we can tell it that we want to stratify our sample when we're making it based on sale price. And you can specify not only what variable you're going to stratify on, but also how many breaks. So like in that last example, we can specify 4 breaks, but you could do more or less than that as well, depending on the scale of the variable that you are stratifying on. But after that, the rest of the process is the same. You still pull out your training and your testing set the same, still fit your model and make predictions the same. The only difference here is ensuring that when we create this split object, we have a balanced sample. And so we'll make sure that it's balanced on sale price. And you could stratify on other variables, but usually for this type of modeling, we want to make sure that we're stratified on our variable that's being predicted, or our independent variable. All right, so now we're going to talk about some other models, and we're going to fit some models that are not linear regressions. So we'll start with a decision tree. So the decision tree function is going to specify a decision tree model. So kind of like the one we saw several slides ago that was like a stepwise function. So we'll fit one of these models. It has a few different arguments to it. We will not talk about what those do right now. We will talk about that later. So we'll talk about tree depth and min-in and cost complexity. But for now, we're just going to accept the default values to fit this model. So what I would like you all to do is to create a model specification for a regression tree and use the rpart package to fit that model. So that'll be your engine, will be rpart, and then calculate the RMSE. So the code will look very similar to what we did for the linear regression model, but we want to use a decision tree specification instead of a linear regression specification. All right, and once you get that RMSE, compare that to your linear model and see which one you think is better. All right, so let's look at this regression tree. And I will actually pull up my own code to go through this one. All right, so I did not ask you all to do this, but I went ahead and created a new split object using the stratified sampling. You don't have to do that. I just did it to help illustrate how that works. So then to create the model specification, we use the decision tree function. We want to set that engine as our part, and we're going to set the mode again as regression. So we can make that model specification. And if we look at just that, we see that it's a decision tree using our part as the engine, just as we would expect. So then to make fit the model, again, we just use that fit function, and we're going to fit that regression tree specification, our same formula using the AIMS train data. So we can run that and we can see our regression tree fit. So this is what it looks like. These is all the decision rules that it is looking for. It's first going to look at living area between these values, and then the third rule, fourth rule, fifth rule. So you can see the full decision tree that it's going through. And then to make the predictions, the same thing, we put in our fitted object. So instead of LM fit, it's now this DT fit model. Our new data is AIMS test. And the truth, again, is going to be the sale price from the AIMS test data. So we get our predictions. We can then calculate the RMSE. The truth is going to be the price truth column we created up here. And the estimate will be that .pred function that comes from the predict. And so we have our decision tree RMSE, which comes out to 59,119. You all might get a slightly different number. So the decision tree is a random process, so your rules might look slightly different than mine, and therefore your RMSE might be slightly different than mine as well. But that's okay. But we can compare the RMSE from our linear model, which I have is about 54,000 compared to our DT model. So this indicates that our linear model is doing a little bit better job than our regression tree model. Was everyone able to calculate the RMSE from their regression tree model and come to the same sort of conclusions? Yeah, so you can see here, I had slightly different values in the slides because my split object was slightly different. So which observations were in the test set versus the training set, and then how the tree was estimated. So you might see different numbers like this, but in general, we should see that the linear model has a little bit smaller error than the regression tree model. So let's try one more type of model. This time we'll fit a nearest neighbor model. You might have heard of this as a K nearest neighbors. And we will talk about either this afternoon or tomorrow how to pick the number of neighbors. But for now, we can just use a neighbors of 1, and that'll be fine for us. So why don't we go ahead and write another model specification that uses the KKNN package to fit a K nearest neighbors model. And then again, calculate the RMSE for this model and compare it to our regression tree and linear regression models. All right, so let's take a look at this KNN model. So to specify our KNN model, we use the nearest neighbor function. And again, we're going to set our engine to be the KKNN package. And we set our mode to regression. So that's our KNN model specification with parsnip. And then the fitting process is just the same as it was for our other models. We fit that specification. The rest of this code remains the same. And then we just make predictions from the KNN fit instead of our LM fit or our regression tree fit. We still use the same Ames test. And then the RMSE code is the same as well to get that KNN RMSE. And when we compare them, we can see that our linear regression actually did the best out of the three models for at least the random samples that I had. I'm guessing that you all found similar RMSE values, or at least a similar ordering among the models. Does anyone have any questions about these model specifications? I'm hoping what you all are starting to see is that when we're specifying these different models, it's really straightforward to create a model specification and then just kind of plug it in to an existing workflow of fitting and predicting and getting the metrics. Is that kind of making sense how all of this is starting to fit together? Thumbs up. Good. Awesome. All right, so that is the end of our prediction slides. So next we're going to talk about classification. So it'll be similar, but instead of looking at a continuous dependent variable, we'll be looking at categorical. So we're making classification decisions. So let me pull up those slides. Maybe. There we go. It's going to take a minute to think, I guess. All right. I think we're in action. All right, so to start, let's go ahead and open up the classification notebook. So again, that's in your exercises. You can open up 09 classification. I will do the same. All right. Okay. So just to refresh all of us on what our goals of machine learning are, so what we're trying to do here is we want to construct models that make accurate predictions for future yet to be seen data. And as we talked about in the last slide deck, these models do not have to be straight lines. They can be straight lines or curved lines. And we're going to focus a lot in this section on decision trees and talk more about what those are. We fit one at the end of our last set of exercises, but now we're going to talk more about what these are actually doing. So decision trees are used to predict outcomes into specific categories. So it's going to use rules to learn from the splits, and each split is going to maximize the information gain. So you can kind of think about it like this graphic here, where you have all of this stuff coming in together, and then it's going to try and divide out which data point goes into each of these different categories. And so here it's dividing out the colors, but we will be using different data. And so we can use decision trees for a regression type question, just like we did in our last set of exercises. And it says basically, all right, we're going to split the data in these 3 places, and then the predicted values in between these bars or on either side of them are going to be the same. So everyone who's below this yellow bar is going to have the same predicted value. Everyone between the yellow and pink will have the same, or purple, and then everyone between the purple and blue will have the same, and everyone above this blue cut point will have the same predicted value. So again, it's this stepwise type of regression function. So how do we assess predictions in this case? We could use the root mean squared error again. So we could calculate our residuals as just the difference or the distance between each observed data point and that stepwise function. And we get these same values that we saw in our last slide deck, where the linear regression has some RMSE, and then our decision tree model has a higher RMSE. So that's one way we can assess predictions. And we end up with these 2 different models that are both trying to do the same thing. They're both trying to predict our data points, and they do fairly similar, but they have different assumptions that they're making, which is leading to different results. So this brings us back to like, what is a model? Like, does it have to even be a line necessarily? And that's where we're going to talk about also the KNN, or K nearest neighbors model. And the way this one works is it's going to predict the outcome of a new data point by finding the K most similar old data points. And then it'll take the average or the mode of those similar data points. And we can use that for regression as well, as we did in our last set of slides. We fit our KNN model, we can get an RMSE. We didn't talk about this in our last slides, but you can get an R squared for your model. If that's your preferred metric, there's an R squared function from within yardstick. So it's just another metric you can use. And what the KNN model is doing is it says, okay, if I want to predict this point, here are maybe the 5 most similar, these blue ones. And so we'll use those points to predict our new point. But you could have a different 5, or you could have 10 nearest neighbors, or 25 nearest neighbors, or 50 nearest neighbors. And that's going to affect the accuracy of your model, how many neighbors you're using to base this off of. So if you have 1 neighbor, for example, you get a line of predicted values that looks very jagged, right? If we do 5 nearest neighbors, we get something that starts to look a little bit smoother, but it's still pretty jagged based on which points are being pulled into those nearest neighbors. So kind of the smoothest line we can get is a logistic regression. And does anyone know, if you're familiar with logistic regression or have seen these type of models before, why a logistic regression is considered a linear model? Has anyone seen logistic regression before? No, okay. So logistic regression is the same, not the same, it's very similar to a linear regression where you have your different coefficients and you basically just add your coefficients up to get your predicted value. The difference for a logistic regression is that rather than our variable we're predicting being on a continuous scale, it's a binary outcome. So 1 or 0, yes or no, pass, fail, those sorts of decisions. And so when we add up all of our coefficients, we're not getting a predicted score necessarily. We're getting a predicted probability that we're in one of the classes or not. So that's why it's a linear model, because we have a linear set of predictors that we're adding together. But instead of a score, it's a probability. And there is a lot of applications for this type of classification. So for example, I'm going to link to some blog posts here if you're interested. This is a blog post that's trying to classify the Federalist Papers, who the author of them was, either Hamilton or James Madison. So this is one example of where you would use classification instead of a normal regression. You can also think of decision trees as a way to classify people. So this is classifying genres based on different characteristics of songs from the Spotify API. So if you're interested in music data, Spotify has an API where you can get data about the tempo and their danceability, speechiness of each song. So we can use that data to try and classify songs into different genres. And you can also look at, this is a similar type of data. It's like where we would put a like a song that you sing along to. And that's based on like the size of the venue, whether the concert's on a weekday or a weekend, whether it's live or recorded. But we're still trying to make a classification decision here. Another neat example is this Shiny app. So Shiny is another R package that we're not going to talk about, but it's basically used to make dashboards, or in this case, an application where you can type in a Twitter headline and it will tell you, we'll try and predict whether that is a Twitter bot or not, if it's a real person. So if you're interested, I would encourage you to go play with that, type in some Twitter handles and see whether it thinks you're a bot or not. But these are all examples of classification. All right, so what makes a model a good guesser, right? There are a couple things. So if we were trying to guess, like if it's like a good example is if you had an animal in your head and you were trying to have other people guess what animal you were thinking of. What's going to make a good guesser is a few different characteristics. The first is you want to have a high information gain per question. So for example, can it fly? If the answer is no, that eliminates a ton of animals. If the answer is yes, that also eliminates a ton of animals. So you get a high information gain per question. Another feature of a good guesser is that you're asking about clear features. So for example, if you ask if the animal has feathers or does not have feathers, that's much more clear than is it small. It's like small is subjective and maybe hard to measure or quantify. So we want to be clear. And then we also want to acknowledge that the order matters here, right? So if you're asking about very specific things early on, that's not going to be as helpful. You want to ask broader questions early to help narrow it down and then get more specific. And so that's what our decision trees and our different methods of classification are going to be trying to do. And I won't make us go through the example of like talking to each other to do our own animal guessing game. But if you were, you would be making a decision tree in that process. All right, so let's look at an example of a decision tree for classification. This comes from the Australian Computing Academy, where they're looking at different species of animals and trying to classify it. And so the way that the tree works is you ask a question like, can it live in trees? If the answer is yes, then you move on to the next question, which is, can it live in water? And if the answer is no, then you go to the next question, which does it have feathers? And if the answer is no, then you land on koala as your final answer that goes in. And so you see that by asking these different questions, you make this decision tree, and then at the end, you have your predicted category. And so in the decision tree, these questions are called features. And in our data, these are going to be the variables. So this is, if you've ever heard the term feature selection, this is what it's talking about. What are the questions we're going to ask? What are the dividing points that we're going to use to make our categories, or at least make our predicted categories? This beginning piece is the root. So that's where your tree begins. All of these different decisions that get made are nodes in your tree. And then the pieces at the end are the leaves. So it's like the end of your trees. Those will be our categories. And again, you follow the path through the answers to your questions, and that gives you your predicted outcome. And so it's kind of like a bonsai tree, or just any tree really in general, but upside down. So you start with the roof or the root, you branch out, and then you end with the leaves or the categories. So it gets smaller as you go down instead of bigger. All right. So take a couple minutes in the chat and to think about this. What type of data are we looking at with each of these different categories? So on the far left, we have a turtle, a snail, and a butterfly. In the middle, we have an unhappy, an okay, and an awesome, a bee that's doing awesome. And then on the right, we have a T-Rex and a shark. Like, what kind of data would you categorize these as? All right, does anyone have any guesses on what type of data we're dealing with here? Could be categorical. Yes, I agree. So that is for sure the one on the left. We have different categories of animals. Yes, I would also say ordinal for the middle one for sure. And then categorical also for the one on the right, but we could be more specific if we wanted to and call that binary, since there are only two options here that are mutually exclusive. So we have different types of data, and those are going to play different roles in our model. And we'll talk about what that's going to mean. And also, instead of extinct or not extinct, we could have real and not real. And so these horses and unicorns are going to come back a couple times throughout our slides. I can't remember if they're back today, but we will for sure see our horses and unicorns again tomorrow. Okay, so I think we asked this earlier. If you've ever fit a logistic regression model with GLM or in general, I'm going to assume that the answer is no, and that's totally fine. Again, we're not going to talk a whole lot about the specifics of logistic regression or how it works. We're mostly just going to talk about how to fit one of these models in R and then how to assess the output of that model. So we'll talk a little bit about what it is, but mostly we're going to be focused on the implementation in R and how we can use those model results. Okay, and so we do get our horses and our unicorns back today. We were right. Okay. So let's say we have some data. We have, I believe in our notebooks for classification, you should have some unicorn data, maybe. I can't remember now if I did that or not, but that's okay. We'll go through it in the slides. But there are unicorns and butterflies. And so we have 1 or 0 for whether an observation was a unicorn or not. And then with that, how many butterflies we saw. So we have a binary outcome here on the x-axis, and then a continuous variable, the number of butterflies we observed on the y-axis. Right, and we can make a distribution, and we see that horses, we tend to find more butterflies around horses than we do with unicorns, which is maybe surprising to me, but nevertheless, we're moving on with it. And so we could predict, based on the number of butterflies that we see, whether there's going to be a horse or a unicorn there with them. And so this curve that's doing the prediction is our logistic regression model. And so again, over here, what we're predicting on our y-axis is the probability. So given the number of butterflies we observe, what's the probability that we're observing a unicorn or a horse? And so we can see that as the number of butterflies increase, the probability that we're observing a unicorn is dropping, which we would expect given that unicorns tend to have fewer butterflies than horses. All right, so we can also look at the predicted values. This would be the probability that each observation is a unicorn. You can see that there are more pink dots up here and gray dots down here. As we're predicting more horses, the further up we get in the butterflies. And we can also predict the class of each observation. And so this is going to be divided right at 0.5. So 0.5 probability crosses right here at about 27 butterflies. So anywhere there's less than 27 butterflies, we're predicting a unicorn, and they get these pink dots. Anywhere that's greater than 27 butterflies is going to get the predicted class of horse. And we could add kittens to it if we wanted to and make a plot of the number of kittens and the number of butterflies. And we see that the horses and unicorns are not evenly spread. So we tend to have more unicorns down at the lower left. Okay, but enough of that example. So the way that a regression model works in parsnip is kind of what we saw earlier, or a logistic regression model, but we're going to talk about decision trees first. Is we get our parsnip model object and these different splits. So if the number of butterflies is greater than 29.5, it goes one direction. If it's less than 29.5, it goes the other direction, and then it divides on the number of kittens, and so on and so forth. And so we end up with a regression tree model that looks like this. I thought we were done with this example, but it kept going. Sorry about that. So we start at our root, and our first split is on butterflies. So there's the 29.5. If you are greater than or equal to 29.5, you go into the horse category. If you're less than 29.5, then we ask another question, which is the number of kittens. And that gives us another split of horses and butterflies, or horses and unicorns. So the way that you get a classification of a unicorn is to have butterflies less than 29.5 and kittens less than 62.5. Right. And again, this is what that output looks like for a regression tree. Again, we'll see more of this when we start fitting our own models here in a few slides. And so you get your observed data. So this is what it actually looks like. Our number of horses, so the more points there are, the bigger these dots. But when we fit our regression tree, these are what our predictions look like. So everywhere that we have a low number of butterflies and a low number of kittens, we're predicting a unicorn. So right, this point is gray over here because it's actually a horse, but we're going to predict that it's a unicorn. And similarly, everywhere that's above those boundaries is getting a predicted value of horse, even though some of the observed values are unicorns. And so what we are wanting to do as part of our classification is figure out how we can assess these models. So we need a way to compare our observed classes to our predicted classes. And so the RMSE is not really going to help us here because it's not a continuous score. Like, what is the residual from a predicted class of unicorn to horse? Like that, the residual doesn't really make sense in that scenario. So again, we first decide where that cut is going to be. So we have to decide, are we first going to cut on the number of kittens? So we can cut kittens at around like 55 here, or we can cut butterflies at just under 30. So which is going to give us the most information, is going to give us our best first cut. And the decision tree says that the butterfly split is the most informative. So we pick that split. And then we choose our next split. We can, again, split on the number of kittens, say these are unicorns, these are not. Or we could split again on butterflies and say these are unicorns and these are not. But in this case, the kitten split is more informative. And so that becomes the split that we go with. And that's how we ended up with that bottom corner being all pink. Okay, now we are done with the unicorns and the horses for now. They'll be back tomorrow, but not for modeling. When we talk about resampling tomorrow, we'll see our unicorns again. All right, so we're going to be dealing with data from Stack Overflow and the Stack Overflow Developer Survey. I'm not sure whether you all have been exposed to Stack Overflow before or seen it, but if you are doing any sort of programming and you have questions, Stack Overflow is a great place to go to ask questions or to see what questions other people have been asking and the answers. So I'm on Stack Overflow a lot. And one of the things that they do is they do a developer survey. So every year they'll send out a survey and ask people what type of programming languages they use, what kind of job they're in, what their title is, where they're working, and they publish that data every year. And so we are going to be looking at some of this data today. And the specific question that we're going to be looking at is predicting whether a developer is more likely to work remotely or not. So developers can work in their company offices, I guess like pre-COVID, they could work in their company offices or remotely. And what we'll find in our data is that there are specific characteristics of these developers, such as the size of the company that they work for, how much experience they have, where in the world they live, and all of these are going to affect whether or not someone is working remotely or not. And here is just one example. So you can see that as there are fewer employees, people are more likely to be working remotely. So in the setup chunk of your notebook, we loaded in the Stack Overflow data. If you give it a look, you'll see that this has just over 1,100 rows and 21 variables. So you can see we have the country, the salary, whether they work in open source, whether they code as a hobby, as well as for their job, the size of their company, whether they are remote or not. So that's going to be our outcome variable of interest. And then a bunch of other information about their job that they provided in the survey. All right, so we can use initial split again to make a testing and a training set. And this was also in the setup chunk, so this has been done for you. But we will create an initial split object. And again, we're going to stratify on remote since that is our outcome variable. And we can extract the training and the testing sets just like we did before. All right, so now we're going to use these. So using the Stack Overflow train and Stack Overflow test data sets, take a couple minutes and look at how many individuals in the training set are remote and how many individuals in the testing set are remote. All right. So there are a few ways to do this. I will show you one way that is a new function that's part of the dplyr package, but that we didn't talk about, but is really useful for tasks like this, which is count. So if we take the Stack Overflow train data and we say we want to count by remote, that will tell us the number of people that are remote and not remote. And so that's a very easy way to count the number of people that are in different categories within your data. And so we can do the same for our test data as well. We can count remote. And so we can see that we have balanced data, which is what we would want and expect since we stratified based on remote. So count variable is a new function, but is very helpful for these types of things. All right, so we verified that our stratified split worked and we have balanced data. And we can look at just a quick summary to kind of explore our data. So we saw in the bar graph earlier that people in a smaller company were more likely to be remote. And here we can see that people who have more years of experience, so this is the years they've been coding on their job, tend to be more likely to be remote. So we have this remote bar graph, tends to be a little more skewed up toward higher years of coding. So it looks like more experience and smaller company means more likely to be remote. All right, but we're going to start fitting some models to look at this. And we're actually right at a break. So how about this? Why don't we go ahead and take 15 minutes. So we'll come back at 2:45, and then we will start estimating some classification models on the Stack Overflow data. All right, so we'll come back at 2:45 Central Time. Okay, go ahead and give me a thumbs up or let me know in the chat if you are back. We are now in the home stretch for the afternoon. All right, so let's keep going. We're now going to start fitting some models to the Stack Overflow data with parsnip. All right, so this is something we've seen before in our last set of slides. And the process for specifying a classification model is going to be almost identical to how we specified a regression model. So we're still going to pick a model, we'll pick our engine, and then we'll set the mode if we need to. And the mode is really what's going to change here. So again, to pick a model, we can search the parsnip models online to find what we are looking for. We set the engine. So for our first one, we'll use rpart again for building classification and regression trees. So you might have heard this as a cart model before, but that's what we'll be doing here. So we'll use the rpart. And now in the mode, we'll set mode to classification instead of regression. And that's going to tell parsnip that we are dealing with a categorical outcome instead of a continuous outcome. All right, so here's how we would specify our decision tree in parsnip. We use the same decision tree function. We set the engine to rpart. And finally, we set the mode to classification. All right, so let's go ahead and fit a model. So there is some template code in the notebook that you all will complete. So we'll build a tree specification that's provided, and then use the fit function to train that model with the following formula. So we're going to predict whether someone's remote from the number of years they've coded in their job and their salary. And so after you fit that model, go ahead and look at it, remind yourself what that output looks like, and then do some predictions. So predict the remote status with the testing data. And you'll use the same predict function for that. And do be sure to keep the set seed 100 at the start of your code. That will hopefully make sure that we all end up with the same set of results. Okay, so let's look at this regression classification. All right, so we build our tree model with the decision tree function. We specify our part as our engine, and we set the mode to classification. And then to fit the model, we do the exact same thing that we did in our previous examples using regression instead of classification. We use the fit function and our model specification. We specify our formula, which again is predicting remote status from the years of coding on the job and salary. And the data we're using is the Stack Overflow training data. So that's how we fit our model. When we view the model, if it will switch tabs for me. Maybe or maybe not. There we go. And we can see our information about the model. So again, we get information about the amount of time it took to fit the model and the number of data points we had. And we get information about the different splits that are being used. So we're first splitting on salary, 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 and salary. So it appears if salary was the biggest driver here in this model. And then to make predictions, which again is probably going to take a second to flip tabs here. There we go. So again, we can use our same predict function. So we're going to predict using our fitted model. We say that the new data that we want to predict is the test set, so Stack Overflow test. And now instead of a predicted score, we get a predicted class. So whether each row was predicted to be remote or not remote based on their years of experience and salary. Was everyone able to get these predictions? Thumbs up, good. Awesome. Okay. So again, we are trying to construct models that are going to generate accurate predictions for our future yet to be seen data. And we are now going to focus on how to get accurate predictions and how to measure these predictions, like determine how accurate they are in a classification setting. All right. So what I want you all to do now is we want to make a data frame of the observed and predicted remote status for that testing data. So in our last example, we got the predicted values. So now we're going to add the observed values to that, and then use that count function that we saw earlier to look at the number of individuals by their true and remote, or their true and their predicted remote status. And so once you've done that, try and answer these following questions. We want to look at how many predictions did we make total? How many times did we predict a status of remote? How many respondents are actually remote? And then how many predictions did we get right? All right, so we'll take a few minutes to try and answer these questions. All right. So let's look at these predictions that we made. All right. So there are a couple ways to do this. One way would be to mutate the observed values on like we have previously. That's a perfectly valid way to do this. I went a different direction just to demonstrate that there are multiple ways to get to the same answer. So I started with the testing data. I selected only the remote field, so that's our truth. And then I used this bind calls function to add the predictions to that. So there are multiple ways to get to this. This is just one new way to kind of show you there are additional ways to get to the same answer. Right, but once you have your truth and your predictions in the same data frame, then we can start to answer those questions. I don't know why my tabs are being so slow today. All right, okay. So we take our predictions. Again, we can use the count, and we want to count by the predicted class and by the truth, which is remote. We don't have to specify truth here. I just did that so it would be renamed to make it a little more clear which is the prediction and which is the observed. Okay, and so if we're thinking about the questions we were trying to answer, we can look at how many predictions we made in total. That would just be the sum of this in column. If we want to look at how many places we predicted remote, that would just be, again, the sum of these first two, so about 129. And we can also look, I forget the other questions that we were trying to answer, how many respondents are actually remote. So that's going to be the sum of this 89 and the 54. So those are the two remotes from the truth column. And then finally, we wanted to look at how many predictions did we get correct. And so that'd be places where the predicted class and the truth are the same. So it'd be 189 or 89 plus 103. So we got 192 correct predictions and 94 incorrect predictions. All right. So there is a shortcut to do this. Conf mat will create a confusion matrix. This is again part of the yardstick package. This is another metric, but it'll create a confusion matrix or a truth table that has observed and predicted classes. So here, just like our RMSE, we can specify our data. We tell it the truth is in the remote column, and our estimated class is in the .pred class column. And when we do that, we get this nice matrix that shows us for our predicted status of remote or not remote, and the truth of remote and not remote, and gives us a nice matrix that outlines that. There's also a function called autoplot, which will make a heat map of your confusion matrix. So the darker means that there are more cases in those cells. So if you have a highly accurate model, you'd want a very dark diagonal right here, which is what we see. All right, so the confusion matrix, there are different types of kind of metrics we can pull out of a confusion matrix based on the true values and the predicted values. So the top left and the bottom right are places where we made a correct prediction. So we predicted a unicorn and it was a unicorn, or we predicted a horse and it was a horse, or in this case for a minus, we predicted not a unicorn and it was not a unicorn. And then these off diagonals, we have the false positive. So we have a fake unicorn, and we have a false negative, which would be a pony imposter. And so we can kind of group these errors or correct predictions in this way. And so again, we have true positives and false positives on the top, and then false negatives and true negatives on the bottom. And these different types of errors or correct predictions are what is going to lead to our metrics for assessing these predictions. So the first one we can do is accuracy. So this is our number of correct predictions out of all of our predictions. So again, this is our true positives and our true negatives divided by the sum of all 4 cells. So true positives and true negatives. And so we're dividing our total correct predictions by the total of all predictions. All right, so that is our accuracy. We can also look at sensitivity and specificity. These are 2 metrics that you'll see a lot in the classification literature. So sensitivity is looking at just values that are positive in truth. So this is, another word is the true positive rate. So out of all true positives, how many did we predict correctly? The opposite of this is specificity, or the true negative rate. So out of all of the true negatives, how many did we predict correctly? And we can calculate these through the yardstick package. They have a bunch of different metrics, which again, we can look at this link. So just like for parsnip, how there was a page that had all of the different model types on there, yardstick has a bunch of different metrics available, and it'll tell you whether it is for predicting classes, class probabilities, or a numeric. So for example, under numeric, we find the RMSE, which we used earlier. And under class, you'll find accuracy, you'll find sensitivity and specificity as well. All right, so we can calculate metrics for our Stack Overflow predictions. So we can use the accuracy function, tell it that our truth is in that remote column and our estimate is in the pred class column. And we see that 67% of our predictions were correct. We have a true positive rate of 62% and a true negative rate of 72%. All right, but this can get a little annoying, like calling 3 different functions to get our 3 different metrics. So we can do a shortcut with metric set. So we can say for our Stack Overflow metrics, what we're interested in are accuracy, sensitivity, and specificity. So we give all of those to this metric set function. And then if we do Stack Overflow metrics for all of our preds with truth and remote, then it's going to give us all 3 estimates back at the same time. So we can specify early on, these are the metrics we're interested in, and then we can just use one function to get all of our metrics at once. All right, so there's one more metric that I want to talk about today. And that is the ROC curve. So this is another one that's very popular and that you'll see a lot. And this is going to take predictions and return a table with probabilities. And so for the ROC curve, we send it the truth, so whether a person was remote or not. But instead of the predicted class, what the ROC curve needs is the probability that someone is remote or not. Right? But we don't have that in our predictions data, right? We only have the observed class and the true class. So we need some way to get the estimated probabilities out of our model. And we can do that with predict. So again, if we start with our Stack Overflow testing data and get just our remote variable, that's our truth. Then we can bind calls. That's just going to add a column to the end of this where we're predicting from our decision tree. This is going to give us our predicted class. And then we can do this again, except in our predict function, we can specify that the type of predictions we want are probabilities. And so it'll add these two columns onto the end as well. So now we have our truth, which is the remote. We have our pred class from our first set of predictions. And then we have two additional columns, which are the probability that each person is remote or not remote. And if you look through this, you'll find that anywhere where the probability of being remote is less than 0.5, the predicted class is not remote. If the probability is greater than 0.5, the predicted class is remote. So now we have both predicted classes and the probability of each class. And so with that information, we can calculate our ROC curve. So we tell it that the truth is in that remote column and the estimate is in that probability of being remote column. And this gives us a data frame back that has like different thresholds for deciding that cut point between the predicted classes and the resulting sensitivity and specificity. So if you recall on the last slide, I was saying that they use a 0.5 threshold to determine the classes. What the ROC curve is going to tell you is what would happen under different thresholds. So if we used a threshold of 0.368 to determine our predicted class, we would have a specificity of 0 and a sensitivity of 1. If we used a threshold of 0.6, we would have a specificity of 0.72 and a sensitivity of 0.62. And similarly, if we used a threshold of 0.687, we get a specificity of 0.762 and a sensitivity of 0.573. All right. So now I'm going to have you all build that same data frame that we just walked through in the slides. So build up those predictions that have the truth, the predicted class, and the probabilities. And then use the ROC curve function to calculate that ROC data set. And then identify which threshold we should use if we want a specificity of at least 0.75. Okay, so we'll take a few minutes to work on that. All right, so let's go ahead and take a look at our results. So again, here's the code to build up those predictions. And again, we use the ROC curve function with our true status and our estimated probabilities. And we can see that if we want a specificity of at least 0.75, that means we need to be using a threshold of 0.687. So this is very helpful if you are trying to determine how to classify individuals, what probability you should be using. You can use the ROC curve to balance what level of specificity and sensitivity you want, and that will help you guide you in which threshold to pick for that. All right, and so we can also make an ROC curve. So we can plot this. So this is the data frame we were just looking at that comes out of that ROC curve function. And using ggplot, the way that an ROC curve normally works is you put 1 minus the specificity on the x-axis and then sensitivity on the y-axis. And if we look at that, maybe we'll look at it. Well, what you want, oh, here we go, is you want this curve to be pulled up toward the top left corner. So if you do basically just chance guessing, that would be this center line right here. And so the further up toward the left you are, the better predictions that you are doing. And you can also create this plot without typing out all the ggplot code manually. So again, we saw the autoplot function for a confusion matrix. You can also use autoplot for your ROC curve, and it will spit out a curve that looks just like that. And this is a ggplot that comes out. So you could take this autoplot and do plus theme and tweak the theme elements if you want to. This is a ggplot object. It's just kind of automatically making the code for you to build it. Right, so one way we can assess how good these predictions are is to look at the area under the curve. And so again, the further we pull this up, the better the predictions are. And so there's more area under the curve down in this area. So bigger area under the curve, better predictions. So an area under the curve of 0.5. So again, if we just divided this in half and looked at just the bottom half, that'd be 0.5 is random guessing. And then an area under the curve of 1. So if this went all the way up to the corner, you have a perfect classifier. So you're always making correct predictions. And there's no hard threshold, but generally an area under the curve of 0.8 or higher is considered good. And of course, there is a function in the yardstick package called ROC-AUC that will calculate the area under the curve for you. So just a few slides left before we're out of time today. Again, a straight line is going to be guessing. Perfect would go all the way up to the corner. If you are below that middle line, you're doing a pretty poor job of classifying. You're doing worse than you would if you just randomly guessed. This is kind of an okay classifier. We're doing better than chance, but not super great. And this would be a good classifier. It's not perfect, but we have a large area under the curve. All right, and we are almost out of time, so we'll just take 1 or 2 minutes to work on this, and then we'll look at the solution before we are done today. Use the ROC-AUC to calculate that area under the curve. We already have our predictions from the last exercise, so you can use those predictions and the ROC-AUC function to calculate the area under the curve. You can also use the autoplot function to create that curve. It's just 1 or 2 minutes and then we'll come back. All right, so let's quickly look at the solutions for this. All right, so we have our predictions, and again, this includes the predicted class as well as the probabilities. And so we tell it the truth is in that remote column, and the estimate is again the probability of being remote. And we see that our decision tree model that we fit has an area under the curve of 0.678. So it's okay. It's not great, but it does better than chance. And again, if we use the ROC curve and send that to autoplot, we'll get that same area under the curve plot that we saw earlier. All right. And it froze again, but does anyone have any questions about classification? I know that we are right at time. So if you do have questions, feel free to bring those tomorrow morning. Not seeing any right away. Well, we are right on schedule. This is right where we wanted to be at the end of day 3. So thank you all for hanging in and pushing through those last few slides quickly. We will be back tomorrow morning at 9 a.m. Central Time, and we'll be starting with a discussion about some different resampling methods. So we'll talk about bootstrap sampling and cross-validation. So that'll be tomorrow morning at 9 o'clock, and I will see you all then. Thank you again for your time.